Okay, we want to look at separation processes tutorial 4. We'll take the questions one by one. So the question starts by saying that the solubility of a gaseous substance A with a molecular weight of 26 in water is given by Henry's law. So the law is Pa is equal to 10 to the power 5 Xa. Pa is in millimeter mercury. And we are supposed to convert the equilibrium relation to the following forms. So we have Ya is equal to Mxa. That's the first form. If the total pressure is 10 bar. In the second form, we want to convert the relation to is Pa is equal to M prime Ca, and Ca is given to us in gram mole per liter. So we are just trying to convert this relation over here, this relation here, to the other forms that are in the question. And the last part says that also write down the equilibrium relation using the mole ratio units. Assume that the solution is dilute and has a density equal to that of water. The density of water here is 1000 kilogram per meter cube. So we'll take it bit by bit. We have the molecular weight, we have the expression. But the question told us that Pa is in millimeter mercury. And we're given the total pressure to be in bar, right? So we have to make sure the units are consistent. It's either we change the total pressure from bar to millimeter mercury, or we change the expression such that it's no longer in millimeter mercury but it is in bar. And I think it's easier to just change the total pressure so that you don't touch the expression. The expression is as it is, right? So for bar, normally I usually convert to kilopascal before I convert to anything else. I feel like it's because I've gotten used to working from kilopascal, right? But I could have converted this directly from bar to millimeter mercury. So I just change it from bar to kilopascal by multiplying by 100, then divided by 101.3 and multiplying by 760 to get it in millimeter mercury. But I could have gone straight for it. It would have just been the 10 over 1.013 times 760. You could have just done it straight away. So we want to convert this expression here, the one up here, sorry, to Ya is equal to Mxa. So if we look at them, if we compare, realize that Xa is the same, but what is changing is Pa, and it's being changed to Ya. So what's the relation between Pa and Ya? We know that Ya is equal to Pa over P, the partial pressure over the total pressure. So I can make Pa the subject and have Ya times P. And I can put that back into the original expression we have up here. So that becomes Py is equal to 10 to the power 5 Xa. We've already calculated the value for our P. So we can divide through by P and then replace the value of P there. And if we simplify, we should be getting about 13.32894 Xa. So this for the first part. Now for the second part, we want to convert it to this form instead, right? So Pa is the same for both relations, but what is changing is Xa, and it's being changed to Ca. So what's the relation between Xa and Ca? We know that Xa is equal to Ca over C total, or the mole fraction is equal to the concentration of that species over the total concentration. We have a system which is a mixture of gas A and water, and it is very dilute according to the question. So the question even told us that the solution is dilute, and we can assume that the density of the solution is the same as the density of water. It means that the solution is so dilute that we can approximate its properties to be as though it was just water, right? So if you're looking for the mole fraction, it's a Ca over the total, which is Ca plus Cw, concentration of A plus concentration of W. But we are saying that the solution is so dilute that we can approximate the properties of the bulk solution to be that of water. So Ca plus Cw can be approximated to be just Cw. It's as though the concentration of water is so large that the concentration of A added to it is not really having a significant effect if you look at the total concentration. So let's imagine we have um maybe let's say the concentration of A is 0.1 mole per liter, right? And the concentration of water is like, let's say, 1000 mole per liter. If we should add them at the end of the day, we'll have 1000.01 to be the total, but it's very close to 1000, so we can just work with 1000 instead. That's the analogy we are trying to use here. The other thing is that concentration is equal to density over molar mass. So now that we know the density and molar mass of water, we can find the concentration for water, right? So since we assume that the bulk of the mixture is water, we can estimate the total concentration using water's properties. So that would be 1000 kilogram per meter cube over 18 kilogram per kilomole. So if we should simplify, we'll get 55.556 kilomole per meter cube. But from the question, they said the units for the concentration was in mole per liter, right? One thing to note, if you see gram mole, is the same as mole. if you see kilogram mole, it's the same as kilomole. The mass term there doesn't really imply that there's mass over there, right? It's just another way of saying mole. Gram mole is another way of saying mole. Kilogram mole is another way of saying kilomole, right? So if we actually do unit conversion, you realize that the gram mole per liter is the same as kilomole per meter cube. So we don't have to convert this over here to any other unit, right? So we have our original expression. We just found our XA to be CA over CW, and we've calculated CW. So I can replace XA here with that expression, and I'll have this. So if I should simplify, 10 to the power 5 over 55.556 will give me this form, right? So PA is equal to 1799.9856 CA. Now, the mole ratio unit. The mole ratio, if you talk about the mole ratio, it's just the mole ratio. So it's the mole fraction of the species that we are working with, right? Divided by the sum of the mole fractions of every other species in the system. So if I have A, B, C, and D, and I'm looking for the mole ratio of A, it will be the mole fraction of A over the mole fraction of B plus C plus D, right? Or the mole fraction of A over 1 minus the mole fraction of A. So here I see that the mole ratio unit considers the mole fraction of our species of interest relative to the sum of the mole fractions of the other species present. So we can see that this is the relation for mole ratio. So the mole ratio Ya is equal to the mole fraction of A, small ya, over 1 minus small ya. And 1 minus small ya, it just means that you're adding all the other mole fractions of the other species. So if there's B, C, and D, it will be YB plus YC plus YD. That's equal to 1 minus YA, right? I think I should have added the proof for that, but this should be something that we all know. Then when we are done, I'll just quickly type it out so that we get that, right? So you realize previously we had an expression. So let me go back so that we see. Previously we had an expression over here. Ya is equal to 13.32894XA. And our mole ratio is in terms of Ya, and we can get one in terms of XA, right? So what we want to do is from this mole ratio relation, that we are having, we can make small ya the subject. And how do we do that? We want to make it the subject so that we can put it back into the original equation. So how do we do that? We can multiply we can send the 1 minus ya down here to multiply the capital Ya over here. Then if we expand, we'll have Ya minus Ya, right, to be equal to this. Then we can send this part over the equal to sign because it has small ya here. So when we send it over, this is what we are going to get. Then we can factorize small ya out and have it in this form. Then we can make small ya the subject, so it becomes big Ya divided by all of this. So that's what we have over here. We can do a similar thing for XA as well. Now, this was our original equation. We can put this here. This is small ya. This is equal to small ya. We can use it to replace this. And then this is equal to small XA. We can use it to replace this. So that's what we have over here. Then we want it to be something that is linear, right? We want it to look like this in a way. Well, not linear per se, but we want it to look something like this. So I can send the 1 plus Ya down here to go and multiply the other side. So that's what we can see. And I can expand. So this is going to multiply the first term 1 and to multiply the second term Ya. So that's what we have here. When it multiplies 1, we have this. When it multiplies Ya, we have the same expression, but then there's a Ya term here. Then we can simplify it further. So we can send what we have here over the equal to sign. And then we have this expression here. Then if we factorize capital Ya out, because there's Ya here and Ya here, if we factorize it out, we have the expression in this form. So now let's simplify the left hand side. If we simplify the left hand, just the left hand side right now, just this side here, right? So you can find the LCM, which is 1 plus XA. Then this is 1 over 1. So 1 will go into 1 plus XA and we'll be left with 1 plus XA. That will come and multiply 1. So we'll have 1 plus XA, right? Then the denominator here, 1 plus XA will go into itself once. And then we'll have just 1 left. So that will come and multiply the minus 13.329XA. So that's what we see over here. Then if we simplify that, I have XA minus 13.329 XA. So that will give me minus 12.329 XA. And I can relate this now to the right hand side. That's what we have here. Then I can send the denominator here to come and multiply this side. And then the numerator here to come and divide this side. Right? So I'm just making capital YA the subject. So if I do that, this is what I would get. Then the 1 plus XA here can cancel out the 1 plus XA here. And this is going to be our final form. Right? So this is the final form for what we are looking at. Now, let me type out what I was trying to say earlier. So what I was trying to say was, will there be enough space? Okay. So let's say we have YA, we have YB, we have YC, right? And we want to find the mole ratio for A. So all we are saying is that YA is going to be YA over the sum of all the other terms. So that is YB plus YC, right? So the sum of all the other mole fractions. But we also know that YA plus YB plus YC, if we add all the mole fractions, it should be equal to 1, right? So if I want to get just YB plus YC, then I can see that YB plus YC is equal to 1 minus YA. So that's why we are using 1 minus YA as a denominator here, right? So that's the whole idea behind it. The sum of all the mole fractions is equal to 1. But we're only looking at the sum of the mole fractions of the other species, and we are leaving out the one that we are interested in for the denominator. So that becomes 1 minus that mole fraction. That's what we are just trying to say. So we have YA, YB, and YC. The mole ratio for A is YA over the sum of the sum of the mole fractions of the other species. But if we add everything, it should be equal to 1. And if we make YB plus YC the subject, we get 1 minus YA, right? Even if it's just two terms, YA and YB, it still works out. No matter the number of species you have, this expression will still work out. Okay, so that's it for question 1. We'll solve the other questions and send them to you as well. Thank you very much.